Greetings, this is part 1, plotting the signal. So ECG 1 to 4 is being included in MATLAB, where the sampling frequency is being initiated. Afterwards, the period is being calculated by getting the number of data dividing by the sampling frequency. The graph is being plotted in different colors in numbered grid and plot in figure 1, whereas the x-axis is defined to 0 to 10 and y-axis is the maximum value of y. And the graph is labeled with legend. So this is how figure 1 should look like. As for part 2, convolution, here is the initialization for the original signal, x. Here is for the distorted original signal, xs, and here is for the filter. Okay, so after initializing the range for the unconvoluted graph, we will convolute xs signal here and will plot two figures, figure 1 showing 3 subplots which has the discrete time of original signal, the distorted original signal, the function filter, and also second figure will show the convoluted signal. So figure 1 shows x, xs, and also the filter, which when compared to manual is exactly the same. Whereas figure 2, which is the convoluted one, shows also exactly the same.
So this one is a coding shows on how to plot poles and zeros. So we are given equation of filter yn equal to 0.5 xn plus 0.5 yn minus 2. So we use Z transform method to get the zeros and poles, and then we plot the zeros and pole by using Z plane. And this is how it looks when it is plotted on the Z plane. As you can see, there are 2 zeros and 2 poles located at zeros. Next, we are required to plot the frequency spectrum of the signals given for us. So we have to load all the ECG signals that are given. This is the frequency of sampling for each of the ECG signal. And this one is how we find the length of ECG signal. To plot the x-axis, we use this limitation so that the signals is at the center of the graph. And then to plot the ECG signals, we use this, which is 1 over L1, which is the length of the signal, and fast Fourier transform of ECG1. To plot the signals, FECG1 is the x-axis, while the absolute value of fast Fourier transform shift ECG1 is the y-axis. The absolute value is so that the signal is always positive value. And then we repeat for each of the ECG. We repeat the same method for each of the ECG. And this is the result for each of ECG. Next, we are required to plot the frequency spectrum for the filter given in phase 1. So we use W equal to linspace negative pi 2 pi. And then for K, we will vary the value between 1 to 2 and 3. And this one is the numerator and A1 is the denominator. And then we use Z function to plot the filter. And this is how we plot the filter with absolute value so that the filter is always positive. And this is the result. And this one is for K equal to 1, and this one is for K equal to 2 and equal to 3. Basically, K is the number of order for the filter.
In phase 3, we are going to design a low-pass FR filter using Hamming window. We will set the delta omega to 0.02 pi. If we look at the frequency spectrum of unfiltered ECG1, we will see a spike in 50 Hz frequency, and we are going to set the cutoff frequency to 40 Hz. Since we are using Hamming window, from delta omega we can obtain the length of the filter by using this formula. Once we got the length of the filter, we can find the order of the filter, the delay. Next, we will substitute it into the general formula for the window, and we will multiply it with the window, which is Hamming window. Then we will filter ECG1 with the filter that we have created, and we will plot it to see the outcome of the filter. So this is the outcome of the filter. This is the unfiltered ECG1 signal without the filter, and after filtering we can see that there will no longer be oscillation in the filtered signal, and here is the FIR filter that we have designed. This is the magnitude response of the filter. Thank you.